When we have a generally evolving hot temperature distribution stream and also cold temperature distribution stream, more complex analysis is required. So what we might want as an example is we might want a way to define the total heat transfer rate, Q dot here, in terms of the conductance or this overall conductance parameter U, or overall heat transfer coefficient, times the surface area of, for example, the shell side or tube side flow, PL, times an appropriate temperature difference. And so this appropriate temperature difference is an appropriate mean temperature. You'll see that this mean temperature is sometimes called the log mean temperature difference. And so what we want is a way of analyzing problems that are generally more complex than what we might have in a simple saturating flow problem. And so to do this requires a little bit more analysis. What we're going to do is we're going to formulate a differential equation, or two differential equations for that matter, for both the hot side and cold side flows for some delta X region in the heat exchanger between the hot and cold side flows. So imagine that you have a whole hot side flow. So this is a co-flow heat exchanger. A co-flow heat exchanger, the curvature you'll see is more of this type. And so you have a hot side fluid flowing in at some initial temperature and coming out at some lower temperature, TH2, a cold side fluid coming in at TC1 and flowing out at TC2. What we're going to see is that there are two differential equations for both the hot side and cold side fluids. We can combine these two differential equations into one differential equation for the temperature difference between the two flows, and we'll understand better what happens for that problem. So these problems are assumed to be steady state, steady flow. So these are steady problems in which there is no generation and there is no storage. For problems of that type, the differential change in the heat transfer rate can be related to the change in the enthalpy in a mass flow sense, which can be related to the mass flow rate times some specific heat capacity times the temperature difference. This is the type of thing that we've done in a global sense, and it's true also locally. Said differently, one can imagine that the amount of heat that is changed, the amount of heat that is transferred between the hot and the cold stream, which is U P delta X. Remember, P delta X is the area element, so this is a differential area. U is this overall conductance or heat transfer coefficient times delta T is equal to the mass flow rate times the heat capacity times the change in the cold temperature. So the cold temperature increases associated with the heat transfer rate from the hot fluid. And so that makes a lot of sense. And similarly, the hot temperature loses temperature because of its heat transfer to the cold fluid. So the hot temperature decreases. The decrease you can see because of this negative sign. From heat transfer to the cold flow. So if we divide through by delta X for both equations and let delta X go to 0, with an understanding that each of these delta T's is really a T of X plus delta X minus a T of X, that is, we have gone for a differential element, then we get two coupled differential equations. By coupled, what we mean is that we have a differential equation for T hot that is in terms of T cold, and a differential equation for T cold that's in terms of T hot. we're going to use the notation that m dot c is capital C. So this is the overall capacitance. It's capacitance rate in a sense because it's the mass flow rate times the specific heat capacity. And this is just notational to make it a little bit more simple. It's a little simpler, a little more compact. So what we do is we divide each of these equations by the corresponding C. We divide the hot flow by the CH and the cold flow equation by CC. And we subtract the cold flow equation from the hot flow equation. So make sure that you can follow this. Again, what we did just in a relatively simple and fast way is we had dTH dx is minus UP over CH TH minus TC, and correspondingly dTC dx is equal to UP over CC TH minus TC. We subtract these equations from each other. We have dTH TC dx is equal to, and so here's the interesting part, we have minus UP over CH plus a UP over CC TH minus TC. And so this eventually can be rewritten now. We just factor out the UP as dTH minus TC dx minus UP times this capacitance sum times the temperature difference across these two flows. If we divide by TH minus TC, that is, we're separating the equation, so it's making it separable. Then we can integrate this, and we integrate it from the inlet location to the exit location, and this becomes a log of TH minus TC evaluated between the inlet and the exit. So it becomes a ratio of the logs, log TH minus THL minus TCL over TH0 minus TC0 is equal to the integral in X from 0 to L. So it becomes a relatively simple solution in terms of this integral. In terms of these logs, this log THL minus TCL over TH0 minus TC0 is equal to minus UPL. So this is the X at L location. Okay, so we can simplify this by simply understanding that Q dot is equal to equivalently, so this is from the overall energy balance, the overall heat transfer rate is equal to the mass flow rate times the specific heat capacity. Recall that this is m dot H CH, and this is m dot C, C of the cold stream, times their overall temperature differences. So we can substitute for our 1 over CH plus 1 over CL, or CC, excuse me, using TH0 minus THL over Q dot. So in doing so, we come up with an expression for Q dot solely in terms of the heat transfer rate, heat transfer coefficient, the surface area, and the temperatures for this problem. So these are our overall temperatures in the problem, our overall temperature changes. What this does now is it says that Q dot, we've now found what our overall our effective temperature is. Remember, because UPL is sort of comparable to H times the surface area times, now typically we'd say a delta T. In this case, we call this a delta T LM. It's a log mean temperature difference, and that delta T LM is given here as TH minus TC at L minus TH minus TC at 0 divided by the log of this quantity. In cases where we have some average U over the length of the system, then we can sort of define this appropriately. For more complex geometries, there's this F factor that's often found in tables. So this is a tabulated value. For more complex heat exchanger geometry. And so it allows and expands this type of solution procedure to these more complex systems, although the basic ideas are held constant for this problem.